Okay, so this is the outline for chapter 33 about the Maxwell equation and then some of the hardcore physics stuff. So first we'll talk about the Gauss law for magnetic field. Yeah, because we already learned Gauss law in chapter 23. Okay, so there will be another version for the B field. And then the second part is about the induced magnetic field and also the displacement current. So this is an extension for the Ampere's law as the Ampere-Maxwell's law. So in chapter 29 we only learned the Ampere's law. So there is only a single term mu0 I enclosed on the right side. So there will be another term, okay, to make it more complete. So this part is about the displacement current, the second term on the right hand side of the Ampere's law. So and then after getting it, we call it the Ampere-Maxwell's law. And then up to here, okay, so this is enough for your preparation of the final exam. And then for the remaining part is some kind of hardcore physics stuff, okay? So that won't exist in the exam, so just feel relaxed to listen to it, okay? So of course I'm not a physics guy, so I try my best to use up all of my physics knowledge to let you know some of the stories here. Okay, so Okay, so this part is about the Gauss law for B field. Okay, so for B field, so this is to highlight the simplest magnetic structure that can exist in magnetic is a magnetic dipole. Okay, just as what I mentioned in chapter 28, I have already mentioned that. Okay, so the simplest structure. Okay, so the smallest structure. Okay, how you can say. Is a magnetic dipole. We can't have magnetic monopole. Okay, magnetic monopole. Okay, although in some of the theories, some of the physicians try to assume, if the monopole exists, what will the Maxwell equation be? But of course, up till now, okay, we cannot find the magnetic monopole. Yeah, this is contrary to the E field. Okay, for the E field, for the Gauss law for the E field, we have a single charge. Okay, of course we also have electric dipole. Okay, with two charges. Okay, with the same amount but in opposite side close together. This is called the electric dipole. But we cannot have a single charge. If we can have a single positive charge somewhere or a single negative charge somewhere else. So they don't necessarily need to be packed together as a electric dipole. But for the magnetic dipole moment, for the magnetic dipole, you cannot separate into two magnetic monopole. Okay, so this is the fundamental, okay, so building block, okay, to generate the B field. Okay, so in that sense, you can imagine, okay, for the Gauss law for the E field, okay, we have something like this, okay, epsilon naught, and then the surface integration E dot dA equals Q enclosed, okay, so which means that you can just assume, okay, there is a Gaussian surface, and then inside the Gaussian surface you count out, okay, a total charge inside the Gaussian surface. It can be positive charge, it can be negative charge, so that this net charge amount is related to the electric flux. Of course, there is a constant epsilon naught on the left side. Okay, so according to the duality, so epsilon naught will turn to 1 over mu naught, and then the E field will turn to the B field, something like this. Okay, so there is charge for the E field, but there is no electric monopole. magnetic monopole. Okay, so there is only magnetic dipole, which means that how you enclose the magnetic monopole, there is something like positive and negative perfectly cancel. So it turns out to be a zero. Okay, so if there were magnetic monopole, then there will be something non-zero on the right side, and then okay, everything will be different. But hopefully, okay, we only have a magnetic dipole, so that the right hand side is zero. And then as long as the right hand side is zero, so this constant is not important. Okay, so this is not zero, so we can just cancel out. Okay, we can just multiply mu zero on both sides, and then so we only get, okay, so we only get this part to be zero. So we don't need the 1 over mu naught on the left side. Okay, so compare with this one. Okay, so this is nothing special. So how you use the Gauss law for the E field, then how you use the Gauss law for the B field, and then even easier, okay, because the right hand side is always zero, so you don't need to count out the how many magnetic monopole, okay, inside the Gaussian surface. It must be a zero. So okay, so nothing special related to that. Okay, just let you know there is the fourth law inside the Maxwell equation. So this is pretty much it. Okay, so the second part, okay, we introduce another one called the induced magnetic field or induced B field. Okay, it should be induced B field. Okay, as I mentioned. Okay. So so in chapter 30, we know that if we have let's say if we have a coil, and then for this coil, if there are magnetic flux changes, there will be induced EMF, induced E field. Okay, so we can also imagine that for an Amperean loop, okay, if we have some electric flux changes, okay, electric flux changes, there will be some induced B field. There will be some induced B field. So that's what the induced B field here. Okay, so in that case, this law can be written as, actually this part is the same as the left hand side of the Ampere's law in chapter 29. But for the right side, of course, we have this d phi e dt, d phi e dt, and then we also have this mu naught epsilon naught. Okay, so later on you'll know this constant is really important. But okay, just yeah, keep it in mind. Don't try to repeat it too many times. Just yeah, so we have this constant here. And actually, you can compare with a Faraday's law, like this is line integral of the E dot ds will be negative d phi b dt. Yeah, so this is the Faraday's law. So E field change to B field, and then the phi E, E field change to B field, phi B change to phi E. Okay, so B and E exchange. And then, of course, this is negative sign, this is positive sign, okay? And then there's an additional constant here. Okay, so here it says, so as charging a capacitor, so this is an example, okay? So it's just as what I mentioned, this induced magnetic field is related to the displacement current we'll introduce in the slightly later. And so actually it's called the displacement current. And I've mentioned that the displacement current is actually the current going through a capacitor in a circuit theory. Of course, the physician tried to distinguish it. This is not a current, it should be a displacement current because there won't be any electron going through. Okay, so the idea here is that, okay, so this is a current Okay, so in circuit theory, it's a current, but there shouldn't be any E minus, any electron going through this gap. Okay, there won't be any charge going through. It is just like if there is some current going in this direction from left to right, so maybe at the very beginning there are no charge, okay, in this capacitor. So sometimes later there are positive charge accumulating on the left plate, and then some negative charge on accumulating on the right plate. So there won't be any charge going through this gap, and in that sense, okay, still there are some current. Okay, but we'll say this is a displacement current. Okay, it's actually the electron won't go through. Okay, so here it says, as an example of a sort of induction, we consider the charge of a parallel plate capacitor with circular plate. So which means that if we try to cut it here, okay, if we try to cut it here, so this is the cross section for this plane, okay, and then we also assume that this capacitor is a cylinder, it's a circular parallel plate, okay. So in that sense, the charge of our capacitor is being increased at a steady rate, okay. So which means that this current is a constant by constant current I in the connecting wire. Then the electric field magnitude between the plate must also be increasing. So which means that the E field for this plane is increasing. So which means that the electric flux is also increasing in a steady rate, in a constant rate. So which means that, okay, so we have this electric flux changing. Okay, so this is a positive value for this case. So which means that there will be also a positive value for the left side. And then as much as this is symmetry, you also always have this like B times 2 pi R, something like that. Okay, so yeah, so this is pretty much it. I think these 2 pages is mentioning the same thing. So only points here is that because the electric field through the loop is changing, the electric flux through the loop is must also be changing. So according to the above equation, so this point and this point, according to the above equation, this changing electric flux induces a B field, okay, induce a B field around the loop. Okay, so it is something like this. Okay, it is something like this. Yeah. So here is just try to compare this Maxwell equation with the Faraday's law. So they look very similar. Okay, so of course you exchange B and E for these 2 terms, and then there are 2 main differences. Okay, similar. They are similar but different in 2 ways. So the first one is mu naught epsilon naught. Okay, so the permittivity and permeability appears here. Okay, so this is the first point. To match the SI unit, of course, it has even more meaning later on. Okay, I will say that this one, okay, actually relate to the speed of light. Okay, the speed of light. Actually, C equals 1 over mu naught epsilon naught. Okay, so the speed of light. 3 times 10 to the 8th power, or more precisely 299.8 something. Yeah, so 3 times 10 to the 8th meter per second. Yeah, so which is the speed of light. And I'm not sure whether you already know. Actually, the light, okay, the light is a specific type of the EM wave, and of course, this course mainly cover the electromagnetism. So for the Maxwell equation, we can actually use the Maxwell equation to derive the wave equation. And by solving the wave equation, the solution is actually the electromagnetic wave, the EM wave. And actually, the light is a specific type of the visible light is a specific type of the electromagnetic wave. And I think I've already mentioned that in chapter 21. There's a spectrum, okay, from low frequency to very high frequency, like the RF and then the infrared, and then visible light, and then violet, and then even higher X-ray, something like gamma ray, something like that. Yeah, so actually visible light is a specific type of the EM wave, and then of course, okay, so this I mean this constant is related to the speed of light, and of course the speed of the electromagnetic wave. So this is the first point, and then for the second point, there's a negative sign. There's a negative sign for the Faraday's law known as the Lenz's law. But for the Maxwell's law here, okay, so we call this one Maxwell's law, okay, Maxwell's law. So this is a positive sign on the right side. So it means that if we have, for this case, okay, we have external, we have E field, okay, we have E field pointing into the page, and it is increasing in a steady rate. So in that case, this one, okay, will generate B field clockwise, okay, clockwise. So it's just like if it is increasing, so use your thumb pointing into the page, your four fingers align clockwise. Yeah, but for this case, according to the Lenz's law, if B field is pointing into the page and is increasing, so the induced B field should be pointing to the opposite side to counteract these changes. So which means that your thumb is pointing out of the page, and then your forefinger are like counterclockwise. So this is the negative sign, okay? So this is the negative sign causing the opposite direction for the induced B field and the induced E field for the two cases. Okay, so far, okay, in chapter 29 we learned the Ampere's law. The left side is this, and then for the Maxwell's law, the left side is actually the same thing. And then for the Ampere's law, the right side is mu 0 I enclosed, and then for the Maxwell's law, mu naught epsilon naught d phi e dt. So which one we should pick? Okay, so the physician try to pick both. Okay, so yeah, because the physicians are adults. Okay, they try to pick both. So they try to make it like on the left side, integration of b dot ds, the line integral, and then okay, for the right side, just add them together. Just add them together. So this is the static current. This is the static current, the current in the original sense, and then this one is the displacement current. Okay, of course we have not mentioned the displacement current yet, but yeah, if you have some sense of the physics, so this thing equals to a current adding something. Okay, so this one should have the same dimension as a current, so the physician try to call it the displacement current. Must be a current adding a current. It cannot be a current adding a voltage or something else. So combining the Ampere's law and Maxwell's law, we just call it the Ampere's Maxwell's law. Although when I learned the electromagnetism, I just learned the whole thing as the Ampere's law until I read the textbook. Then I know, oh, this is called the Ampere Maxwell's law. Or otherwise, I just know this one as the Ampere's law. Or maybe you find some other material on the from other textbook or from the internet, maybe just call the whole thing Ampere's law. So this is just a name. I don't think it is that important. in my opinion. Yeah, maybe some other physicians don't agree, but yeah, this is fine. Just a name. Okay, I would say. Of course, yeah. So here it says when. So here we have both terms. So how can we simplify it? Okay, so it says when there is a current, but no electric flux change, then the second term will turn to 0, and then it will be reduced to Ampere's law. Okay, and then when there is a change in electric flux but no current, then the first term will be 0, and then it will be reduced to Maxwell's law of induction. So only the second term remains. So this is just to make it more general. So you can just use this thing to handle either case. And then you need to think, okay, there's only static current, no electric flux change, then we only have the first term on the right side. And then if there's no current, but electric flux change, then we only have the second term. Okay. So let's take a look at this sample problem. So a parallel plate capacitor with a circular plate of radius capital R is being charged, and then derive an expression for the B field at the radius R for the case R is smaller than or equal to capital R. So here, as we already know, okay, there's only a magnetic flux change. This is a current. There won't be any static current going through the capacitor. So we can directly use the Maxwell's law. Integration of beta ds equals mu naught epsilon naught, and then d phi e dt. Okay, so yeah, so the left side we don't try to repeat it again and again. So it turns out to be b times 2 pi r. Yeah, according to many symmetry. Okay, the b and the ds points to the same direction. So b dot ds will be b times ds, and then b will be uniform for the whole circular Ampere loop, and then okay, it turns out to be a multiplication for this integration. Okay, so I don't try to repeat the steps. Okay, so on the right side, mu naught epsilon naught, and then d. We also know that, okay, we also assume that the E field between the parallel plate are uniform and also parallel to the dA. So it turns out to be E times A. Or originally, this thing should be something like this. Okay, no this. Okay, should be like this. Okay, no circle for the integration sign, not a closed surface. But turns out to be, this thing turns out to be E times A, and then dt. Okay, something like this. So A is a constant, so mu naught epsilon naught A, and then dE dt. And then finally, okay, it is a circle, so pi r square, and then dE dt. Okay, so actually we get b times 2 pi r equals mu naught epsilon naught pi r square dE dt. So we can actually make some cancellation. Cancel this pi with this pi, cancel this r partially with this r square. So finally, B equals mu naught epsilon naught small r over 2 and then dE dt when r is smaller than or equal to capital R. Okay, so this is the expression. This is the expression, just like what we have done for the Faraday's law. Actually using it for the static current. Okay, we have derived something like this. Okay, so here it just lets you evaluate the B field when R is equal to capital alpha 5 and then d dt equals to this value. So actually, B equals mu naught epsilon naught R over 2 and then d e dt, and then you plug in a number, 4 pi times 10 to negative 7 for the mu naught, and then 8.85, so 8.85 times 10 to negative 12, and then R is this one, 11 times 10 to negative third power, all over 2, and then times 1.5 times 10 to the 12th power. So this is 9.18 times 10 to negative 8 Tesla. Okay, so this is just to plug in the number in the expression that we derive. So for question C, derive an expression for the B field at the radius. Okay, so the only difference is that here is R is larger than capital R. So similarly, we have this whole thing to be the same, but there's something different. So on the left side, it is still B times 2 pi R. And then for the right side, mu naught epsilon naught. And then this one turns to be E times A. But here the A, okay, the A is only pi capital R squared. And then we also have this d e dt. Yeah, because only the capacitor, the area, I mean the region between the capacitor have E field. The region outside the capacitor, we assume the E field to be perfectly zero. So that this A only cover pi capital R square, not small r square. So finally, we can only cancel this pi with this pi, and then we have B equals mu naught epsilon naught capital R square over 2R, and then d e dt. So yeah, so I think we have already derived similar formula before, yeah, in chapter 39. Okay, so just as what I mentioned, for this Ampere Maxwell's law, the right side for the first term, we already know that it is a current, and then for the second term, at the very beginning, the physician don't know how to call it, okay, but as a common sense, you can only adding the current with a current. You cannot add a current with something else. So they know that that one should be a current in some sense. And then finally they call it a displacement current. Of course, in a circuit theory, we will say that this is just a current for a capacitor. In a circuit theory, yeah, but the physician tried to distinguish it with a normal current, yeah, because there won't be any electron going through a capacitor. As long as there are current going into the capacitor, and then there is another current going outside for the other terminal, it is just accumulate some charge for the plate, okay, accumulate some positive charge on one plate and then accumulate some negative charge on the other plate. So there is no electron going through the parallel plate, okay, so going through through the vacuum, or something in between. Maybe there could be some other material inside, okay, just as what we learned in chapter 25. So maybe there can be some dielectric, but it's just yeah, but actually the free electron cannot really go through. Okay, so here we just call it the displacement current. So in that sense, we can just write it as ID. The displacement current is defined to be epsilon naught d phi e dt. Okay, and then finally, if we use the notation of the displacement current, it can be written as mu naught I enclosed plus mu naught ID enclosed. So, or actually mu naught I enclosed plus ID enclosed. So nothing special, just make it like a current adding with another current. Okay, so yeah. So if we actually use the notation of ID, okay, it can be like here we have a capacitor, and then as much as we have a current. So if it is inside the capacitor, so here we have R is smaller than or equal to capital R. So we have this formula. Okay, we have actually derived the same form in chapter 29. Okay, so you can just check it back. We have already derived something the same. But for that case, it is a static current. Here, we just consider it as a displacement current, and then it turns out to be the same form. If it is outside the capacitor, then it is just like this. Okay, so I think you should have memorized it. Okay, mu naught I over 2 pi r. So because it occurs very often. So you should be able to memorize it. Okay, so here is another sample problem, so that we can just control the displacement current. So here it says the circular pair plate capacitor is being charged with a current I. So between the plates, what is the magnitude of the B dot ds in terms of mu 0 I at the radius r, blah, blah, blah. Okay, so so here we have a integration of B dot ds equals mu 0 ID enclosed. Okay, so just make use of the displacement current notation, and here it is inside. Here is inside, and also we assume the current density is uniform. So in that case, ID enclosed over ID is actually pi r square over pi capital R square. So this is the whole displacement current for the whole capacitor, and then this is just we assume the ambient loop, okay, with a radius of a small r, so that ID enclosed only enclose this smaller area, smaller circle. So in that case, integration of B dot ds is actually mu 0 ID, and then so actually mu 0 ID times R square over capital R square. So we just try to move ID to the right side and then cancel pi and pi, so that turns out to this one. Okay, actually this one is actually this thing. Okay, and then we have mu 0 I actually here you just call it I. Okay, so ID is actually I, so we have R over 5 square over R square. So it turns out to be mu 0 I over 25. So this is the final answer. It didn't tell you what is the I. Okay, so for the question B, it says in terms of the maximum induced B field, what is the magnitude of the B field induced at R equals capital R over 5 inside the capacitor. So BR equals mu 0 ID over 2 pi R square and then times R. For this whole thing is actually proportional to R, okay, proportional to R. So which means that BR over B max should be BR over 5 over B capital R, okay, because when R is larger, okay, so B is also larger. So the maximum B field should occur for when R is equal to capital R. So and then it is nothing but 1 over 5, okay, because they are linear relationship. So which means that the BR is actually B max over 5. Okay, finally, let me just wrap it up and then we can have a break. So up till now, just as what I mentioned, if we need to summarize, okay, so if we want to describe electromagnetism in 2 words, I'll say this is Maxwell's equation. And actually, inside the Maxwell equation, there are 4 laws. Okay, so none of them are called Maxwell's law, okay, none of them are discovered by Maxwell, okay, and at very least, okay, Ampere's law we will call it Ampere-Maxwell's law. So half of the 4 laws are contributed by Maxwell. So why does it call Maxwell equation? The idea here is, of course, Gauss has discovered the Gauss law for electricity, Gauss law for the magnetism. Okay, so they are the laws, to let you become calculate the B field for some of the structure, and then also the Faraday's, okay, found the Faraday's law, can let you calculate the induced E field, and then of course the Ampere's law or Ampere-Maxwell's law tells you, okay, if there are some current or some displacement current, okay, there will be induced B field. So they just occur individually. So finally, Maxwell tried to summarize, okay, of course, for the electromagnetism, we have even more laws than this 4. Let's say the Biot-Savart law or maybe the Coulomb's law, okay, we actually have learned much more than these 4 laws. But Maxwell's just summarized that if we really need to solve for any problem related to the electromagnetic field, these 4 laws are sufficient. Okay, these 4 laws are sufficient to solve anything, okay, related to the EM field. So in that case, this is the contribution of Maxwell. So finally, we call this Maxwell equation rather than Gauss equation or Faraday's equation or Ampere's equation. So we just call that Maxwell's equation. Okay, so these 4 equations explain a diverse range of phenomena, blah, 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 blah. Okay, so I don't try to talk too much.